Welcome to Rishiraj's PhD thesis defense. A quick bio. He joined IIT Gandhinagar as a PhD student in 2019 after doing his BTech from Guwahati University, and he's currently working as a research scientist at Geo Platforms Limited. He's a finalist for the Ubicom Caetano Porello Outstanding Student Award and received the Fulbright Fellowship in 2022, for which he went to Carnegie Mellon University to work with Professor Mayank Goyal. He was also the Prime Minister Research Fellowship awardee in 2021, and 2024 participated in the 11th Heidelberg Laureate Forum. He is primarily focusing on health sensing and ubiquitous computing. So for this particular talk, it will be roughly an hour, including question and answers. Initially, he'll give the talk. The committee members, some of them have joined online, including the external committee member, Professor Rishiraj Sen. And so after he's given the talk, the committee members and the students can ask questions. After which, Rishiraj will be asked to show the revision document, which was the thesis comment reviews, if he has addressed them properly or not, that will be shown. And post that, Rishiraj will be asked to leave the room for a couple of minutes while the committee decides on the fate. So over to you. Thank you.
Yeah, thank you, Professor Nipun. I hope I'm audible across online to the offline audience.
Yes.
Okay, thank you. I'll get started with my presentation. Good afternoon, everyone. So today we are going to talk about respiratory disorders or respiration rate and respiration rate. So chronic respiratory disease is a worldwide problem. In countries like the United States and India, 2,000 years of lives are lost per million population owing to respiratory disorders. We know what is respiration rate. It is the number of breaths you take per minute. And respiration rate is an important biomarker to diagnose respiratory illness. In patients, unrecognized changes in respiration rate is also associated with poorer health outcomes. For example, disease and conditions like stress, anxiety, pneumonia, cardiac arrest, or even COVID-19 can actually be predicted with irregular respiration rate. But respiration rate is hardly monitored in clinical or even at home. For example, if you go to a clinic, the doctor might check your heartbeat or your heart rate using a stethoscope and even your temperature using a thermometer. But the check for respiration rate is completely missing from the scenario. Even modern wearables like smartwatches and smart rings, they do an excellent job in sensing heart rate or even step count, but respiration rate information is missing, particularly fine-grained respiration. They detect respiration only when you are asleep. In my PhD thesis, I investigated techniques to sense breathing and use that breathing information for wellness and diagnosis. With respect to wellness, I developed a system which is known as Joulesy, which estimates energy expenditure from respiration rate. With respect to diagnosis, I developed two systems. One is Apnea-I, which again uses respiration information to diagnose for sleep apnea, and Spiromask, which uses respiration information to measure lung health. First, I'll focus on my first project, which is Joulesy. If we talk about Joulesy, it is about estimating energy expenditure. But what exactly is energy expenditure? In simple words, it is the number of calories we burn when we do exercise, certain kind of exercises. And the gold standard machine of measuring how much calories you have burned or the energy expenditure is a device known as indirect calorimeter. The person on the right is wearing an indirect calorimeter, which is a machine which is composed of a mask and is connected to a device. It is a bulky device, cannot be carried around. So the way this machine works in a very overall picture is that it estimates heart rate and the net difference of oxygen content in the blood, and uses both these information to have an estimate of energy expenditure, which is accepted at clinical setting. But even smartwatches do the same. But although they're excellent, as I said, excellent in step counting and heart rate, they're not very accurate when it comes to energy expenditure or calorie burn. Prior research and even our own work has shown that the estimates of energy expenditure from a smartwatch is about 37% wrong compared to an indirect calorimeter. But why they are so hugely wrong? It is because smartwatches rely only on heart rate to monitor energy expenditure. And heart rate, as we saw, indirect calorimeter does a better job there. So on one end, we have smartwatches, which gives inaccurate energy expenditure estimation. On the other end, we have indirect calorimeter, which gives accurate energy expenditure estimation because it monitors O2 concentration. Now, JoulesEye is a system which is more accurate compared to a smartwatch, and it is obviously more practical to use compared to an indirect calorimeter. Now, JoulesEye is a system in which we retrofit thermal cameras into smartphones, or even we can integrate thermal cameras into smart watches. Now, I'll try to attempt to show a demo, and hopefully I'll be able to successfully show it. So what I want to show is what JoulesEye system is composed of. So I've attached thermal cameras, one thermal camera, and this is my thermal feed that you can see on the screen. This is me, my spectacles are visible. Okay, we have lost, okay. And what we're going to do is, we're going to okay, so I'm just having problem with the Zoom screen here. Just allow me a few seconds. Yeah, and I'll fire the, okay, so I want you to see on the left of the screen, which you can see my thermal feed. On the right, there is a graph going on, which is basically showing nothing right now. It's a noisy signal. So what we do in JoulesEye is that we concentrate on the nostril area of the person. So what I'll do is I'll let the algorithm concentrate on the nostril region. And let me see. So now the algorithm is looking at the nostril, and I will stop speaking for some time so that it can track my respiration. So what you just saw is the respiration rate signal as a periodic pattern that you saw on the screen. And if I remove the region of interest, it again becomes a noisy signal. So this is what exactly we leverage in JoulesEye. I'll stop the demo now. So what we just saw is a thermal feed. And in a thermal feed, what we do is, in this case, I'm manually adjusting my nostril into a region of interest from where I can actually extract out the respiration by summing the pixels around the area. And in JoulesEye, what happens, we do this dynamically where the algorithm keeps on tracking the nostrils. So this is what I just showed, that there is a nostril. And because of the evaporation, when you exhale and when you inhale, there is a temperature difference in the nostril. And that temperature difference becomes visible in the thermal feed. And that is what we leverage in JoulesEye. But we just said that JoulesEye is about estimating energy expenditure when you are doing some kind of activity, particularly cycling or running. But when you run, there is a vigorous movement that is happening on the screen. And what I just showed is I was stationary and I was tracking my nostril, but that is not the case in real world setting. So there is a challenge of tracking the nostril when there's a lot of vigorous motion. One simple idea here is to use some kind of facial landmark detection algorithms. These are very prominent in deep learning frameworks. And there are spatialized models which are trained exclusively on thermal imagery to track facial landmarks. So we thought we will use that. But when we use that, if you see the extreme left frame, these are frame by frame, the first frame, the second frame, and the third frame. This is the first frame, second, third. So if you look at the first frame, the nostril is correctly localized here. There's no problem here. But because of vigorous motion, the motion is so vigorous that from the second frame onwards, the model fails to keep up with the tracking of the nostril. You can see the nostril and the landmark at two different positions in this region. And it becomes worse as the movement keeps on happening. In this case, in the third frame, the landmark has completely lost track, and this error just keeps on building up over time. So clearly we cannot use, currently we cannot use a facial landmark which is designed for thermal imagery. But we could also use optical flow algorithms. Now there are a lot of advancement in optical flow algorithm, and this is one of the snapshot where the researchers from prior work shows that they are able to, this is a slowed down version of a video where they claim that they are able to basically detect vigorous motion using an optical flow tracker. But when we apply such algorithms directly to our thermal feed, and here we want to track the nostril, it is not able to track the nostrils. It has completely lost track. This is because thermal image in itself doesn't have a high texture information, which means they do not have high frequency information for the deep learning models to learn. Also, thermal image are not actually images. They are kind of a heat maps. They are of a temperature points in the image. So the way you might decide to represent the thermal image might be different from the way I try to show it. And hence, there's clearly a deep learning domain adaptation problem going on here, because the one which is trained on one, if a model is trained on one kind of thermal image, it might not suit the other kind of thermal image which is collected. So what do we do? So we use a classical algorithm which is known as a discriminative correlation filter. So in this algorithm expects that you provide the algorithm a first initial frame, so at least one frame where the nostril is clearly visible, and tell the algorithm this is where the nostril is. It then simply performs simple correlation in the frequency domain for all subsequent frames to find where that object is. There is also a concept of spatial reliability. It makes a probability map and tries to determine where the object would be in the subsequent frame, and then it keeps track of the nostril. Now this works excellently well in our case, and this woman is having a lot of vigorous motion as she's cycling an ergometer, and you can see as she moves, comes in front of the camera, goes back, the object tracker is still able to keep track of her nostril. And then we just sum up that region and extract out the respiration rate, as I just showed in the demo. So that's about how we extract the respiration rate. Now how do we go to energy expenditure from respiration rate? So here we use a temporal convolutional network, which is a very a general form of a wavenet architecture model, where we estimate volume of exhaled air from the respiration rate, not the respiration signal, from the rate of it. And then once we have the volume, we again use the same temporal convolution network, this time with different parameters, to again go to the energy expenditure. So we get the energy expenditure estimate from this entire approach. Now we performed a user study where there were 54 participants. Some of them performed cycling in ergometer, and some of them performed running in a treadmill. There was a decent representation, above 40% of female participants. And what we found out was interesting. So whenever these people when we were collecting the data, we also asked these people to wear a commercial smartwatch, because what we wanted to see is how much calorie burn does the smart watch predicts, and what is the number of calories burned our system predicts. So what we found out, just like prior studies observed, is that the energy expenditure estimate of the smartwatch is the mean absolute percentage error is 37.6%. Prior work predicted it to be 37%. But when we use respiration rate information and model it through the Joule size system, we found that the error drastically reduces to 5.8%. So what we also found out is that smartwatches do a very poor job in participants with overweight BMI. It anyway does a poor job with all participants, which is 37.6, but people who have abnormal BMI, they're more wrong, 51.8%. But Joule size performs fairly equally for both kind of participant. This is problematic because I believe that the person who will rely on smartwatch are the people who are kind of overweight and would love to lose weight. So now the thermal camera that I just showed you, which is connected to my phone, this is currently quite costly. It costs about $200 to $300. So that is a 256 pixel thermal camera, and we saw that its error is 5.8%. We thought, why not replace this with a very low resolution thermal camera, which is cheaper, and see how much results do we get. So what we found out is that the error, if we use a low resolution thermal camera and track the nostril and do the same thing as I showed in the demo, the error jumps to 15.4%. Now, this is still better than the 37% error that I mentioned, which smartwatches usually have. So it's still better. But then if we use a 24 pixel thermal camera, we could also use the heart rate information, because if we integrate this thermal camera into a smartwatch, smartwatches already have the heart rate information. So we can use both this information, and now our error comes down to 10.1%. It's still doing better. Now I'll quickly show a GIF where it shows this is the thermal camera integrated into the smartwatch. And this is low resolution. Here you cannot see my face. You cannot distinguish whose face this is, but you can still see the respiration rate in the screen that I showed. So you can see the respiration rate in this part, which is extracted out from the thermal imagery. And these are the thermal representation in different heat maps. So we can still use a low resolution thermal camera and still extract out the respiration rate, albeit with a little higher error. So that is about the Joule-Sci project. What we showed here is that, what we found out is that respiration rate is a better predictor compared to only heart rate alone when it comes to estimating energy expenditure. And conventional fitness tracker might be doing a poor job in estimating energy expenditure or calorie count of people who actually needs it, are particularly those people who are overweight or have abnormal BMI. So with that, I'll now move my focus and shift my focus to diagnosis. I'll talk about the project Apnea-I. Apnea-I is about using a thermal imaging system for lightweight and accurate sensing of sleep apnea. But what exactly is sleep apnea? Sleep apnea is a disorder which is characterized by pauses in breathing. So when a person sleeps, the person tends to stop breathing momentarily for 10 seconds to as long as 50 seconds. And then cessation of breathing is a serious problem, as we will see in subsequent slides. So what happens during sleep is that this is how the normal airway looks like. But when you sleep, in some cases, due to obesity or some other confounding factors, the airway tends to get obstructed during sleep, and hence you're not able to inhale and exhale, and this the airflow stops. Now, sleep apnea is a global problem. It is estimated that about 1 billion people suffer from sleep apnea throughout the world. And that is not the only problem. Some researchers estimate that more than 80% of these cases probably remain undiagnosed, because it's not easy to diagnose sleep apnea. But then, how does one diagnose sleep apnea? Before going to that, we'll see what are the risks associated with sleep apnea. So because of sleep apnea, people might suffer from cardiovascular disease, impaired brain function, or even depression. Now, the tree map on the right shows the global burden of different kind of diseases. Now, why I'm showing this, if you concentrate on the top left squares, which is labeled IHD, stroke, HHD, and RHD. So there we have, these HDs are heart disease, different kind of heart disease, ischemic heart disease, hyperventive heart disease, rheumatoid heart disease. And you can see this entire square covers a big portion. This is a big global burden of disease, and it is #1 cause of disease. And heart diseases are immediate consequences of sleep apnea if not treated on time. Hence, diagnosing sleep apnea early is extremely important. But how do we diagnose sleep apnea? So if a doctor suspects that you probably have sleep apnea, you will be advised to undergo a test known as polysomnography test. The polysomnography test is a test where you are instrumented with a bunch of sensors, and you need to go to a sleep clinic and sleep for the entire night so that these sensors can detect your body, different kind of body vitals. In particular, on the left, if you see, there are brain activity, eye movement, and so on and so forth. But the American Association of Sleep Medicine, in its report says is that sleep apnea should be diagnosed with nostril airflow signal and the thoracic abdominal signal. So nostril signal, as I showed, is the nostril airflow which is happening, and thoracic abdomen signal is when you breathe, there is expansion and retraction of the chest wall. So this is the signal, these both signal we need to diagnose sleep apnea. Now apnea eye, our system, is a wireless system. It does not require anyone to wear anything on the body. So this is the image we captured in one of the hostel room in IIT Gandhinagar, where the apnea eye system is placed strategically at the end of the bed so that it covers the nostril. It can see the nostril as well as it can see the abdomen of the person, because those are the signal we are interested in. Now I've shown this before. We do the same thing here, just like Jules' eye. This is a zoomed in version of the person sleeping, and you can see that the nostrils glow like light bulb because of the evaporation that is happening around the nostril, and we can extract out the temperature, the respiration rate from this, from that region. But there is a challenge here. The first challenge is kind of what's solved in Jules' eye, where we extract out the respiration rate from the nostril, but how do you extract out the respiration rate from the movement of the abdomen? That's a challenge. So what we found out during our pilot study is that when a person sleeps, if they could sleep either with a blanket or maybe without a blanket. Now what happens is that if you sleep with a blanket on, your blanket is never straight. It kind of has wrinkles in its surface. The surface of the blanket which is touching your body is warmer compared to those wrinkles which are not touching your body, are colder. Now these hot and cold regions, what happens is that they form what is known as a thermal dichotomy. Dichotomy just means a thermal difference. And when you sleep, when you do a normal breathing, these hot and cold regions tend to vibrate because your body is vibrating. Now we can leverage signals from these regions to extract out thoracic and abdomen movement. But again, the question is, how do you identify such regions? For that, we use the gradient information in the image. We basically take the gradient vector, which is basically the resultant of the the horizontal gradient and the vertical gradient and the horizontal gradient. And once we have the gradient information, there are a lot of gradients in the picture, but then we need to threshold them, threshold these gradients, and we pick up only the high intensity gradient changes. And if we pick up the high intensity gradients, these are the spatial regions from where the movements are apparent, right? I forgot to mention that even when you are not wearing a blanket, this becomes an easier case, like in the image on the right, because now your bed is cold, in a very colder temperature, in a body's warmer temperature, so there is a stark difference in the border. So this is easier problem without a blanket, easier problem to solve relatively when there's no blanket. So now in this image, we are no longer looking at the nostrils, but now we are looking at a specialized region from where we are trying to extract out the respiration rate. And if you have figured out the region, there is a small square box in the place that I'm moving my pointer. There's a small square box here from where we are extracting out the respiration rate. And this is the respiration rate due to abdomen and the thoracic movement. But that's not the only challenge. Once we have the respiration rate, now by this time we have two respiration rates. One is nostril respiration, one is thoracic abdomen respiration. But then the challenges are, how do we keep track of the nostril and abdomen at different sleeping position, because the person will be tossing and turning at the middle of the night and the positions would change. So how do we take care of that? So remember, unlike the Jules eye problem where there is lot of vigorous movement, in sleeping position there is no vigorous movement. The person is kind of in a rest. In this situation, we can actually leverage deep learning, state-of-the-art deep learning models to extract out regions. So we are interested in the nostril region and the abdomen region. So we can ask the deep learning model at different sleeping position to extract out these regions for us. And once it does that, we can then extract the respiration rate. So the first problem we can solve using a ROI localizer, which is in this case a YOLO model, you only look once model. But there is another problem. This time, when the person is asleep, the person might be doing different kind of activities. For example, they might scratch their head, or they might have sleep apnea patients generally tend to vibrate their body a lot during sleep. So what do we do in such cases? So in such cases, we just remove such noisy part of the signal, because what happens if we do not remove them is that the respiration rate tends to get very noisy. So we need to remove such segments. Now, in the next slide, I'll just briefly explain how do we remove this noise. So if you concentrate on the left region, there are multiple frames, thermal videos, and what we do is we use a frame differencing. So frame differencing is simple. So if you look on the image on the B, here the person is sleeping. On the next frame, the second frame, where my pointer is, the person has actually moved his finger and is scratching his head. Now there is a sharp difference between the first frame and the second frame. So if we just do absolute subtraction, we will see that the pixel values won't be closer to 0. There will be some pixel values that will be going on there. And that gives rise to a rise in the absolute difference, which is highlighted in this region. Of course, there could be other frame where there are more vigorous movement and it has led to rise in in the absolute difference. So what we do is, when we detect such regions, we remove them from the signal, and that ensures that the respiration rate that we finally extract out is clean and it is devoid of noise. Okay, so now we have two signals. One is nostril airflow, the blue one, and the green one is thoracic abdominal movement. So this is where we have successfully extracted out respiration signal. But now what we have to do is we have to detect the apnea events. So how do we do that? So first let us understand some apnea events which has occurred in this signal. The one which I have highlighted, if you look at that region, you will see that the periodic pattern in the nostril signal, in the blue signal, is missing. It is also missing in the green part of the signal, which means that the person is no longer breathing from the nostril, as well as there's no thoracic movement happening. This is known as a central sleep apnea event. This is one kind of apnea, this is central sleep apnea. This happens because the brain has stopped sending signal to the body to breathe. And this is a dangerous condition. This doesn't last long. As you can see, the person very soon after starts breathing again. But the damage is already done because you're not consuming as much oxygen as you should normally. This is one kind of apnea. The other kind of apnea is the one region which is highlighted in blue. So what's happening here is that the nostril airflow, the periodic pattern in nostril airflow is gone, but you can still see that there is some amplitude, some movement still happening in the thoracic chest displacement signal, the abdomen signal. And what's happening here is that although the nostril airflow has stopped, but the chest is still trying to push the air out. This happens because when there's an obstruction in the airway, and this obstruction occurs when you have obesity or you have some other kind of genetic disorder which is blocking this airway while you are asleep. And in this case also, soon after, because the body is magical, it self-corrects itself, the body wakes you up, and as soon as you wake up, your airway opens up and you start breathing again. But again, here also the damage is done because again, you're not consuming as much oxygen as you should. And there are other kinds of events. This is hypopnea, which is marked in orange or yellow. So this is same as obstructive apnea, but the only difference is that here the magnitude of reduction is not as high as obstructive apnea. In obstructive apnea, the entire signal is gone, which we by definition say 80% reduction in signal, but in hypopnea it could be just 20%. And we also have a small gray marker here. This is where the signals is completely missing, and these are the cases where the activity happens, and we cannot handle those signals, so we remove them. So to evaluate apnea-I, we did a deployment in 3 different sites. One at AIIMS, New Delhi. The deployment is still ongoing as we speak. There is at IIT Gandhinagar, and even we went to home of some sleep apnea patient and deployed our apnea-I system at their homes. And in total, there were 44 participants. We had over 300 hours of recording, and we detected a total of more than 3,800 events. So this is how the setup at AIIMS New Delhi looks like. So if you look at the lower end corner, the person is actually wearing a polysomnography machine. And we also have our apnea eye system installed parallelly because we want to do a one-to-one comparison between both the systems. And on the right, there is the small screen by which our investigators who are at AIIMS New Delhi can look at the screen and determine if the recording is going on correctly or not. Now, here I have introduced two more graphs to the additional two graphs that I showed earlier. So earlier I was showing apnea eye, the second graph, and the last graph apnea eye, but now we also have graphs from the ground truth PSG signal. Now this is the signals captured by the gold standard machine. And to evaluate apnea eye, we need to have a one-to-one comparison. We need to know if the events that were flagged by PSG machine are also flagged by our apnea eye system. Now in this case, in this snapshot, we had a good one-to-one correspondence, but we have a lot of participants. So what we do is we looked at precision, sensitivity, and specificity of these events for apnea eye and hypopnea, for apnea and hypopnea. And we have some numbers there, but then how to contextualize these numbers? How do we know these numbers are good or bad? To understand whether they're good or bad, we rely on a different metric which doctors rely on. So the PSG machine generates a report and the doctor looks at the report, and doctor is interested in one particular metric to determine whether the patient has apnea or not. And that metric is apnea hypopnea index, AHI. This is number of apneas and number of added with number of hypopneas divided by the duration of sleep. Now, you will be treated as having severe apnea if the AHI score is greater than 30. You have moderate if it's 15 to 30, and so on and so forth. Now we want to check what is the categorization or what's the severity classification of apnea eye compared to the PSG ground truth machine. So when we do that, we found that for most of the participants, our categorization aligns exactly with the categorization of the PSG signal. In particular, if you look at patient 3, 4, 3, 2, 8, we have our systems, the ground truth says it's severe, and we also tend to say it's severe, and so on and so forth. But there are some cases where our classification is not exactly correct. For example, in patient 1 and patient 2, the ground truth machine says they have mild apnea, but our machine says they have moderate apnea. But even in such cases, we never underestimate the severity. Apnea eye is either correct or always overestimates the severity, which is not a problem, because if we are saying someone who is having mild apnea, severe apnea, the person anyway needs to get treated. So that was about my project apnea eye, which is a cost-effective, also privacy-aware system. It uses a low-resolution thermal camera to diagnose apnea. And the most interesting part of this is that it does not require any kind of body instrumentation and can be used for longitudinal studies because you don't need to wear the sensor each and every time. Including the patient, the previous slide I showed patients only, the patient at AIIMS, but if we consider all the patients across the IIT Gandhinagar campus, all the participants across IIT Gandhinagar campus and other home tests, the severity classification is correct in 89% of the cases. And also the remaining months classification, we assign them to higher severity classes, which is not a serious problem, as I just mentioned. That was about my project apnea eye. Now I will spend some time on my third project, which is about SpiroMask. Now SpiroMask is a system. So before going there, we'll start with the motivation, why do we need SpiroMask? So this is mainly motivated by the fact that a lot of people, especially in countries like India, a lot of people suffer from lung disease like chronic obstructive pulmonary disease or asthma. And unfortunately, most of these, as I said, occurs in countries which are affected by pollution, like India, Pakistan, and so on. And what the doctor, if the doctor suspects that you have some kind of lung ailment, the doctor will ask you to undergo a pulmonary function test or spirometry test. Now, to undergo a spirometry test, you'll go to a PFT clinic, pulmonary function test clinic, and use a machine something like this, which is a spirometer. And what you will do is you will forcefully exhale into this machine. And what this machine will record is at what rate are you exhaling your breath and how much total air you have exhaled. So that information is then embed it into this curve. So the y-axis of this curve is the flow rate. At what flow rate are you exhaling? And the x-axis is the total volume of air that you have exhaled. Now, once we have this graph, a doctor is interested in different points in this graph. For example, what is the peak flow that you attained, which is peak expiratory flow? What is the total volume that you have exhaled out? So these are the metric that doctors are interested in. But a very seminal work has happened in spirometry, and one prominent of them was smartphone spirometry, where researchers has replaced spirometer with a smartphone, where now you can just blow air into the smartphone and the spirometer curve will be generated. But smartphone suffers from a major problem, which is smartphone heterogeneity, where not every microphone is same, and not every hardware filters or software filter is same, and hence they're not inherently designed for healthcare. So every smartphone might give different results, which is problematic. So what we did instead is, during COVID-19, we found out that suddenly, and even for places like air pollution, mask is suddenly a wearable that we can leverage to solve the challenges faced by smartphone spirometry. In particular, now we don't have to care about heterogeneity if we place a microphone inside the mask. Or in smartphone spirometry, the another challenge is that how long you hold your smartphone, because the longer you hold, the recording will be going to be different. So here, because the microphone is kind of embedded inside the mask, you need not care about the distance between the microphone and the mask. So the way this works is, we place this microphone inside the mask. We tried with both N95 and cloth mask. And if just 2 minutes, I'll try to show another demo how this recording takes place. So what I'll do is, I'm using my earpiece instead of a mask. I don't readily have a mask. The microphone is similar, like I'm holding one microphone right now, and I'll just kind of mimic a forced breathing and see what happens. Yeah, so this is not exactly correct because it depends on the maneuver. On the left side, you can see that the left side is the raw audio recording. There are noises which I did not filter. And the right side, you can see this is kind of approximate a flow volume curve, where the system is trying to predict what flow you are exhaling out and what is the total volume. I've intentionally removed the x and the y axis because this is just recording and then doing a process known as Hilbert transformation, which is here, to get the envelope of the signal. But then after doing that, after getting the envelope of the signal, you need to use a machine learning algorithm to learn the transfer function between the flow volume of the spirometer as well as the audio recording. So, but the basic idea is that it takes the recording and just makes an envelope, and then you need to learn the transfer function. So not only that, that was about forced breathing, where you need to use a spirometer, you do a forceful maneuver, which is not easy to do, which requires some kind of training. But because you're wearing the mask, we can also keep on recording your normal breathing all the time. So this slide basically shows how we evaluated normal breathing. We asked the person to wear mask, and then we also strapped a phone to record we could have used a chest belt, but we did not have one. So what we use a phone as a chest belt, and then we recorded if the breathing rate associated with the nostril matches the vibration in the chest. But there is a challenge here, because when you're wearing a mask and moving around, you might be speaking, or there might be inherent noise due to the ambient noise. So to deal with that, what we did is we used a 1D CNN, where we window the signal and extract some features and learn a one-dimensional convolutional neural network to basically now break the audio down into whether it is speech, whether it is noise, or whether it is clean breathing audio. That is what we do. And for all the clean breathing audio, we extract out the respiration rate. So in this study, there were 37 participants. Some of them had lung ailments. These are mostly young people in the group. And for the forced breathing, this is a dense result. But what it shows is that if you look at the left one, this is the overall error for all participants. The middle one shows the error for participant with lung ailment, and the right one, the extreme right, is without lung ailment. So if you look at the left, there is a red horizontal line, which is American Thoracic Society's standard for an acceptable criteria of diagnosis. So we saw that the random forest regressor that we use is consistently giving lower error below the red margin, which means that Spiromax, the way we designed it, is an acceptable form of performing lung diagnosis. And it same is true for people with lung discomfort and without lung discomfort. So for all of them, the error margin is below the standard that we need. Not only that, for normal audio, I was telling that we need to classify whether it's speech or not. So for 97.5% of the cases, we saw that tidal breathing is classified as tidal breathing. In some cases, it is not. And we also did some ablation studies where we kind of reduced the sampling rate of the audio. So initially, the sampling rate is 16,000 for the audio sensor, but then we reduce it and see how it affects the error on the right side. So this is important to do because when someone is wearing a mask, you want it to be battery powered and you want the battery to last longer. You do not want it to charge it again and again. So reducing the sampling rate and having the same result ensures that we have a longer battery life. That's the summary on Spiromask, where we designed a system to record forced breathing and normal breathing. It works well for both N95 and cloth masks. So we are almost at the end of the presentation, but before ending, I would want to say something about the challenges we faced in all these projects, Spiromask, Julesci, and apnea-I. So first is deployment of health sensing system where it is required is a major challenge. For example, in apnea-I, finding apnea patients, negotiating with doctors, and then doing this deployment, going to AIIMS, New Delhi, and doing this deployment is very hard. It's not easy. And more than the technical challenges, these were the technical challenges that we faced, like finding a doctor. I spoke to 6 to 8 doctors to negotiate, and then we had a common ground on which we did this deployment. Similarly, for Julesci, you must have seen the slides on indirect calorimeter, but the actual gold standard is captured by a direct calorimeter. But direct calorimeters, you will only find them in hospitals in a very confined room, and not every hospital has that. For example, no hospitals, to the best of my knowledge, in Gujarat has a direct calorimeter because it's not often used. People rely on indirect calorimeter. So these are some inherent challenges that I believe my research, it's some common thing that we will keep on facing from time to time. But the main contribution of this work is that respiration sensing is a solved problem. People have done respiration sensing using different devices. But what I did was that I showed using thermal camera that what do you do with this respiration rate? How do you use it? In this case, I have shown that you can do accurate estimation of calorie burn. You can also do a diagnosis of sleep apnea. And so on and so forth. So we have, my thesis has kind of expanded the application of sensing respiration rate. And also it has shown that there might be some researchers which have solved problems like making spirometry more accessible. But then when we consider new wearables like mask, it suddenly makes the entire research more widely acceptable or more widely available, because now with a new form factor or a new form factor of doing that, recording that audio, you can now suddenly probably scale the diagnosis to multiple people. That was the main contribution. And if we look forward, what next from this entire thesis? One thing is that my thesis is mostly concentrated on sensing. And many researchers do sensing and try to solve sensing in a hope that sensing will give us more information, and this information will be useful in doing intervention. But sensing itself becomes so complicated that we never reach to intervention. So I propose in future that we need to think backwards. Rather than going from sensing to intervention, let's first think about what intervention do we want to exactly do. And once we had decided that, then design the sensing system backwards. Because for example, in apnea-I, we saw that we know who has apnea, who doesn't have apnea. Question, does my research try to treat these people, diagnose, beside diagnosis people? We don't know. So, and second thing is, if we talk about sensing, we need to really think about scaling them. Many researchers do that very successfully well. I aspire to scale these devices. If we are not able to scale apnea-I to at least to 2,000 to 3,000 beds, then it is a futile exercise. So we need to again rethink the design of the system so that we can scale them. With that, this is my end slide. With that, I thank you all for attending, and that was all about my presentation. Thank you, and I'll open the floor to questions. Thank you.
We can first have some questions from the offline audience.
Online audience, do you have any questions?
No, I think I asked when I reviewed the thesis, and I really want to comment because it's not easy to do this level of working with patients and humans. So yeah, it's a great effort. And I have asked my questions in my reviews, and even though they were minor. Thanks, Rishiraj.
Thank you, ma'am.
Any other online questions? Okay, so I'll request Rishiraj to now go through the comments.
Yeah, sure.
So I had one question in the June side project.
Right.
So I think you answered this question when you were talking about your last year, which is Pyromas, where you talked about how the sampling rate
Yeah.
affects the error. So my question was that in the study, does the latency affect the error rate, particularly from the June side project?
Latency, you mean? Yeah, okay. I'll just confirm the question once. By latency, you mean the latency of the thermal video feed in the Joule side project?
Yes, and even the processing part, like because you are tracking the instance,
Right.
and I assume that the processing is happening on the device. So, and as you are targeting small scale devices, does this processing latency
Okay.
affects the error rate, particularly from the first two projects?
Right, okay. I'll repeat the question for the online audience. The question is, does latency, particularly to the Joule side project, does latency affected? By latency, she means latency in maybe in the recording the video or the way the entire processing happens, the time taken to process it and retrieve the final result. So first of all, Joule side, the results that we showed is using a high-res thermal camera, which is 256, which is the standard camera. And we did all the processing offline. There's no online processing going on. So hence, we did not encounter the problem there. But when we moved to the low-resolution thermal camera, which I showed, one of the GIF that I showed in one of the slide, there it's using a low-resolution thermal camera, and it is all the processing is kind of happening, I can't find the slide, but all the processing, yeah, this one. So all the processing is happening on device. Like the respiration, and here, yeah, in this one, this particular image. So here the respiration has been extracted kind of online itself, and then is feeding. So yes, here we do suffer a problem known as dithering because the data rate at which I'm retrieving the signal from the serial monitor is much lower than in this case, than the vibration that is happening on the frame. So for example, the camera cannot, so there is a kind of a jump in frames. If the actual frame is going from frame 1 to 10 in say 1 second, I'm actually seeing 1, 4, 8. So I'm not seeing all the information, and that is the reason the error increases. Otherwise, the respiration rate is already there. So at some points, it's like the signal is heavily downsampled, and because of the huge downsampling, we suffer error. At that point of time, we really did not know how to solve this problem. I still do not have a good answer of solving this problem. But yes, with embedded devices where the processing needs to be faster, we do have this latency issue. Yeah.
Okay, if there are no other questions, I request the students.
Okay, if there are no and it will now be a discussion between Rishiraj and the panel members.